Thanks for the introduction, first of all, and also thanks for you all for coming. It's very nice of you, and also it's nice of you guys of having me here and giving me this opportunity to talk to you about this research. It's going to be mostly about oceanic transfer faults and how they slip and why we study the slip of oceanic transfer faults. Why is it important for our understanding of slip on faults in general? And then at the end, or maybe last 10 minutes, I'm going to talk about something that is not really seismology, or it's a little bit related, something that I got sidetracked on during past months, and I have been quite excited about it, although it might have no meaning at all, but you will see, and I'll also play some sounds of it. So oceanic transfer faults, a very brief introduction into them. Those are faults that connect offset spreading ridges. So when we have spreading ridge in the ocean and there are gaps in between of them, they are normally connected by these oceanic transfer faults. And it's a pretty common type of fault worldwide. So these are the yellow lines here are plotted oceanic transfer faults that are longer than 75 kilometers globally. So we have them on a mid-Atlantic rise. We have them on in the Pacific Ocean. In this area, those are the fastest ones. They may reach up to 14 centimeters per year of a slip. And the one that I study is up there, but I will show some close-up on that later. So why we study them is because they are very special for several reasons. First of all, this is kind of like a section, a long strike section, or an image of a fault. And the seismogenic slip is limited commonly by a 600 degrees isotherm, which extends commonly down to the mantle. So it's not that common that seismogenic faults would slip both the crustal and mantle part, but for these faults, they do. So we have a crustal part. The crust is very thin. In oceanic crust, it's like 7 kilometers in our case. And then we have a lithospheric mantle that behaves in a brittle manner. And then at 600 degrees, we have brittle ductile transition, and we no more released any slip in the seismic manner, but everything slips aseismically. They rupture commonly in earthquakes up to about magnitude 7, and these earthquakes are quite special because commonly they have high number of foreshocks, which is not, we can sometimes see it on subduction earthquakes too, but it's not that common. So people have actually showed that there's certain kind of predictability, both long-term because they occur quasi-periodically, and short-term because there are those high foreshock rates. So also because they release maximum magnitude 7, the seismic cycle is very short. So we can see that time between two large consecutive earthquakes is sometimes it's 4 years, sometimes it's 10 years. In our case, it's like 14 years, but still the seismic cycle is by an order of magnitude shorter than seismic cycle, for example, for many subduction zones. In Cascadia, subduction zone, it takes 300 years, and in here it's much faster. And also, in general, they have oceanic transfer faults have really low seismic coupling, meaning that although I've said that this is the brittle part, not all the energy is released in a seismic manner. It's actually only globally, it's only about 15% is released during earthquakes, and 85% is released during some kind of a slow slip motion or creep or something like that. So the thing we don't really know, that's to this point we understand oceanic transfer faults, but we don't really know how these mechanisms, how the slow slip or creep interacts with seismic slip, and if there is any kind of interaction at all, if there are zones of a creep, or if there are, how is distributed on that seismogenic zone. So those are questions that I would like to address today, and that are primary questions of the research that I'm doing. The area that I'm studying, or we are studying, is the Blanco Transform Fault zone, which is situated in Northeast Pacific. This is when we have United States here. We have Washington, Oregon, and California. So, and Juan de Fuca Plate is subducting underneath the North American plate. The fault, the Blanco Transform Fault zone, is 350 kilometers long, and it's a like intermediate slip rate. So it's slipping in about 5 centimeters per year velocity. This might be a little more conventional look at the situation. So we have the Juan de Fuca plate, Juan de Fuca ridge, and the Pacific plate. And the Juan de Fuca plate is subducting obliquely underneath North America. And in order to compensate this gap between the Gorda ridge and the Juan de Fuca ridge, we have this Blanco fracture zone in here. If I don't explain something clearly, if I'm too cryptic about something, please feel free to intervene and ask me questions during my talk. So don't hesitate to do that. A little bit close up on the Blanco Transform Fault zone. It was created during the last 5 million years from 2 short oceanic transform faults that kind of rotated clockwise during those 5 million years. And so it translated that pure strike-slip motion into something a little bit more complex, and it opened up pull-apart basins along the length of the Blanco Transform Fault zone. So right now we distinguish 6 different parts of the fault. From west to east, we have West Blanco and East Blanco Depression and Surveyor Depression here, which are all 3 of them have some component or large component of transform of strike-slip slipping, but also some kind of extension in there. So those are like pull-apart basins. As we can see, they are quite deep in here. Then we have Cascadia Depression that is probably something that is called a short intra-transform spreading center. So that was left out from those, from that rift zone that was in the middle between those 2 oceanic transforms. And then we have Gorda Depression all the way on the east, and that is again some kind of transform pull-apart basin kind of thing. The only purely strike-slip segment that we have in here is the Blanco Ridge, which is about 100 kilometers long. And my study that I'm going to be primarily talking about today concentrates at that part of the fault because it's very simple in structure, and as I will show you, it behaves quite in a kind of in a predictable manner. About past research done on the Blanco Transform Fault zone, this was Jochen Braunmiller and John Nabilek did this study in 2008, and they relocated teleseismic earthquakes that occurred on Blanco Transform Fault zone between 1964 and 2008. It's about 126 events, and they the magnitude range is from about magnitude 4 to 6.5. But what is a little bit more important than just the epicentral map of that is calculated slip and calculated slip deficit on a fault. So this is about this line here at those 5 centimeters of a slip rate every year. That's about what we would expect in long term that the fault would produce seismically if it was fully coupled. So everything that's lower in this eastern part or the western part, it means that not all the slip deficit that is being accumulated in there during the interseismic period is released in a seismic manner, but there's some kind of a slow slipping or creep motion down to that 600 degrees isotherm that is calculated from some kind of thermal modeling. So we can see that the western part is significantly lower in seismic coupling than the Blanco Ridge. Although the Blanco Ridge, at some parts, this is probably like mislocation. It can't really release more energy than is being accumulated in there. So it's kind of rough, but still it gives us some kind of an idea that the western and eastern part of the fault behave slightly differently, or differently, and the mechanisms are different. So that's pretty much the motivation that was the motivation to pull this project and deploy this network of 54 ocean bottom seismometers on the ocean bottom. The network consisted of 30 broadband stations and 24 short period stations. All of the stations were recording on at the rate of 100 samples per second, and it pretty much covered the area of the fault with some stations directly on the ridge. that might be interesting from the point of view of waves that are actually traveling through the fault. So it collected quite a nice and big data set that I'll be talking about today. These are the instruments. The broadband instruments were Gralb's CMG3Ts with 120 seconds corner, and then we had Mars Products L28 as short period sensors with a 4.5 Hertz corner. Those are the frequencies that I'm primarily using because we don't have that many big earthquakes, and for the local seismicity, normally the corner frequency for those earthquakes is down to about 2 Hertz or 1 Hertz, maybe for the strongest earthquakes. So this is how the OBS packet looks like. So these instruments are normally enclosed in this OBS packet, and there's also a differential pressure gauge. So we have kind of 4 components. We don't have only the seismic components, but we also have a pressure, which shows up to be quite good for earthquake location too, because the P waves translate nicely in the water in that pressure wave that is detected by the differential pressure gauge in there. And I will show you the data. So this is how the deployment looks like. So we have a research vessel oceánu. So we have a couple of them at the university that are kind of shared in the area of universities, and you put the OBSs on board, and then you go wherever you want to go, take a crane and drop it overboard. It sinks down, sits on the ocean bottom, and then you can communicate with it acoustically. And in a year after the memory fills up, you come again with the boat, you communicate with it, you ask it to release and drop weight that is holding on the bottom, and it pops up ideally. But we were pretty lucky during this project, or I was in the field just once on this project, but they were pretty lucky that they were having really high recovery rate of those stations. If it doesn't work out, you need to send a submarine or something like that to recover the station. So it's much more of a hassle if it doesn't pop up, but I think it happened just once or twice. So moving on to results, these are our earthquake locations. As you can see, those dots are quite big, and they are color-coded with depth, but they line up nicely with the structures, with the bathymetry of the fault where you would expect them. And I will show some close-ups on that. Little bit of technical information on the catalog. We recorded and located about 7,700 earthquakes that were detected to more than 10 stations at the same time. So we want to ensure that the quality of earthquakes, because we are trying to draw some tectonic conclusions from it, that the quality of earthquakes and the quality of locations is as good as we can get. We used antelope automatic procedures for both picking and grid searching the earthquakes and location of earthquakes, and then we enhanced it by cross-correlation and relocated everything by HypoDD. I'm sorry for those of you that are not familiar with these seismological tools. I'm just saying it for those that I know that from seismic department there's many people and people really familiar with these methods. So so sorry for those that I can't really go in detail in here. We have the resulting catalog is about of a completeness 2.2, which means that we are quite confident that we recorded pretty much every single earthquake that was stronger than that. So these are event magnitudes or earthquake magnitudes, and these are number of earthquakes. And how it would normally work out is that there would be logically more earthquakes of small magnitude, but because we have some spacing between the stations and we can't really capture all the small magnitude earthquakes, we can only record every earthquake that is stronger than 2.2. And the depth-wise, most of the earthquakes occur in the crust, but there are also some mantle earthquakes. And again, I will show a little bit more of that at next slides. The overall B value, which is kind of a ratio between small events and big events, it's 1.12, which is quite close to global average, but it varies in different parts of the fault. One more slide about quality control of the catalog. The magnitude of completeness is more or less stable over the region. It increases a little bit at the edges of the network, which is kind of logical because we are running out of the network. So we have slightly lower quality of the data set at the edges, but in time it's quite stable. We can say that there were no major breaks in the network, so it's quite okay. How am I doing time-wise? Is there some clock in here? I don't know how fast I should go.
I think you are doing very well.
Okay. Yet. So to show a little bit more of the earthquake location, although I haven't finished this analysis yet, and I haven't used this data for any kind of conclusions yet, or for any kind of tectonic analysis, but I would like to show you how precise the locations are. When we close up on just the western part of the Blanco fracture zone, we can see that the earthquake locations, when we plot them in a smaller size of dots, they are nicely lining up with the faults that we would expect from the bathymetry of the area. So when we have the West Blanco depression, there are probably two major active faults that are running next to each other that are displayed in this cross-section. They are slightly tilted southwards. And there might be one more. This is kind of like an ancient fault that probably used to be active, and now it's being abandoned, and all the slip is moving northwards. But still, we have these two nicely pronounced faults on this West Blanco depression. On the East Blanco depression, it's slightly more complex, but still we have some kind of, because of the rotation, we have some kind of strike slip faulting in here, and then probably something like opening that pull apart basin in the middle. Also, there was a huge earthquake swarm at the beginning of our deployment in here, which might have some triggering mechanism that I'm not really sure about yet, but there is potentially quite interesting, there are some interesting things about that. And also the Surveyor depression is again two well-pronounced strike slip faults running next to each other with some seismicity in between. And the same thing zooming to the eastern part. There is Cascadia depression that has the deepest seismicity that we observe on the Blanco fracture zone. And it's there's actually, I did some focal mechanisms for those earthquakes, and there's actually quite a high number of normal faulting mechanisms. So it means that that the primer motion is actually it's opening up. It may be either that intra-transfer spreading center, or there's some kind of normal faulting in there. And then we have the Blanco ridge, which is, as I said before, is 100 kilometers long, and it's purely strike slip. And the fault, when you display it in a cross-section, it's really cutting the lithosphere down to about 12 kilometers very narrowly, and like a knife. It's really pretty clear cut. And then moving to Gorda depression on the very east, we have again some kind of pull apart basin earthquakes, and then strike slip that is going all the way to Gorda ridge on the very east. So these are the earthquake locations. As I'm saying, they are still waiting for some more detailed analysis that I haven't done yet, but I'll have to do soon. And this is actually the major part of the talk today. This is the thing that has been finished and published, and it actually takes only, or concentrates only, on the Blanco Transform Fault in the middle in here. And so it's about 130 kilometers long, depends where we constrain, where we put the sites or boundaries. It's relatively high seismic coupling, as I showed at one of those figures before, and it hosts the strongest earthquakes on the Blanco Transform Fault zone. In total, we have 5 earthquakes since 1960s that were stronger or equal to magnitude 6. And after relocation of those earthquakes, we see that they fall to 2 asperities that repeat every 14 years approximately. So those earthquakes are highly, or are quasi-periodic, and they reoccur at the eastern at the western asperity, there were three earthquakes in 1981, 1994, and 2008. And on the eastern asperity, there were two of them in 1985 and 2000. So we did the earthquakes location, or we took the locations from the whole data set, and we got about 1,700 earthquakes at this fault that are between magnitude 1 approximately and 5.5. And what's actually interesting and quite important is that about 1/3 of those earthquakes occur in seismic swarms. That in here, we define seismic swarm as events that are pretty close to each other, both time-wise and space-wise, and they don't have any apparent main shock. So there is nothing, it's not like a main shock aftershock sequence, it's just a pretty consistent seismicity over the period of several hours, let's say, 30 minutes to several hours, during which there are somewhere between 3 and 50 events. So when we plot to show that the area where the earthquakes nucleate is actually very small, I show this section, 30-minute section of one swarm that is having about 10 or 11 events in those 30 minutes. And I take just the stronger ones here, these 5 events, and I plot the waveforms and I overlay them on each other. And you can see that on station on the ridge is like a nodal station where the P waves are coming, and they are really tiny, so the match is not perfect. But on those stations away, a little bit in like angles where there's a stronger P wave, we can see it's almost perfect match, that those earthquakes in swarms really occur very close to each other. And in total, we see 58 swarms that range from 3 to 50 events, as I was saying. This is quite an important figure. It displays a long strike section along the fault. And so this is the along strike distance and the x-axis. And then on the y-axis, it displays how deep the earthquakes are. With the gray, I'm showing here the crust, which is going down to 7 kilometers. And then this is the mantle part of the fault. And as you can see right away, those events that are red, the swarm events that I plot in red, they almost all of them fall down in the mantle. And there are a couple of exceptions, but pretty much all of them fall in the mantle. Also, what is quite important here is that I plot several different 600 degrees isotherms. So the top one is calculated by half-space cooling model. So as we go further from the ridge, the plate is cooling down. So the 600 degrees isotherm is actually deepening over time. And we can calculate that 600 degrees isotherm through different models. The easiest one is the half-space cooling model. The problem with the half-space cooling model is the fact that it doesn't really include or consider hydrothermal cooling, because there's probably quite a bit of water circulation through the crust and maybe even through the upper mantle. And it cools down as it descends down and comes back up. It cools down the lithosphere. And that half-space cooling model doesn't really consider that. So this is a Emily Roland model, includes this. So it shifts the 600 degrees isotherm a little bit deeper. The problem still is that we don't really know what the permeability of the crust is. So we think that when we display the earthquakes, we actually believe that based on seismicity, the 600 degrees isotherm is even a little bit deeper than predicted by those two models. As I was saying, the swarms, the events occur in a really small area, or nucleate in very small volume. Although they don't nucleate exactly at the same place, we can actually display them, and we can display the time on the x, and we can see that and this is a long strike distance, and we can see that the events in swarms actually migrate along strike. We can constrain velocities of those hypocentral migration for many of those swarms, and the velocity is somewhere normally between 100 meters per hour and 1 kilometer per hour. There has been observations of swarms together with creep events on transfer faults on land, and they show that whenever swarms migrate with these velocities, they are normally triggered or related to those creep events. So what probably happens is that we have some small asperities that are behaving in a brittle manner, and they are surrounded by a creeping part of the fault. And whenever the fault creeps, it triggers those asperities and triggers those swarms. So that's actually what we believe is happening in here. And from one of those strong earthquakes, 6.5, it's not an earthquake that we would observe in this year during our deployment, but one of those historical earthquakes. And from centroid depth, we can do like a back of the envelope calculation, assuming that the crust is fully coupled. We can actually calculate what's likely to be coupling of the mantle part of the fault. And it is about 40%. So 40% of slip or energy in the mantle is actually released during earthquakes, during the seismic slip, and 60% is released aseismically during creep. So why we think actually that the mantle part of the fault can host both the aseismic and seismic kind of slip is because we believe that it has been altered to serpentinites in there. As I was saying, the fracture zones or even normal oceanic crust provides quite a bit of, it's like a natural pathway for water circulation. So water goes down and then it may alter, it cools down the lithosphere, but when it reaches the mantle depths, it's actually capable of altering that to serpentinite. And serpentinites are quite strange materials seismic-wise because they can behave based on the slip rate, based on how fast we move them. They can behave both in a seismic manner and both in an aseismic manner. So when we have a fault that is created from or with some component of serpentinites in there, when we move it really fast, the frictional force is actually going to drop, and it will allow an earthquake or like slip, like a fast slip, to occur. So that's called velocity weakening mode, that with increasing velocity, we are actually dropping the frictional forces, and we are allowing for earthquake to nucleate. Whereas when we move it very slow, it behaves in a velocity strengthening manner. So like whenever it moves, but it moves slow, the frictional force increases, which doesn't allow for any nucleation of earthquakes or seismic slip. So it actually creeps. The only kind of motion it can just creep. So, and then the asperities might be patches where the water didn't reach, so they are still dry, or maybe the serpentine dehydrates back to olivine in the mantle. One more kind of interesting observation: the strongest earthquake in the data set was magnitude 5.5 on the Blanco Fault, and right before that, this is the depth on the vertical and time on the horizontal, and we see like very small on the free events swarm coming before the magnitude 5.5 earthquake. And we think that this might actually explain why people historically have seen a lot of foreshock sequences before earthquakes and oceanic transforms, is because there might be those episodic creep events that trigger swarms that actually appear as foreshocks before large earthquakes. So maybe I was too cryptic now, but let me rephrase this in this final model that we formulated in here. We think that the fault actually looks something like this. This is the crustal part of the fault that is fully seismically coupled and releases all the slip in a seismic manner. And then this is the mantle part of the fault above the 600 degrees isotherm that should normally behave in a seismic manner, but because there is high water influx and serpentinization, it actually releases some energy in a form of episodic creep. That episodic creep releases about 60% of that energy, and there are those small dry patches of dry olivine that can still produce some earthquakes. So whenever there is an episode of a creep that takes somewhere from tens of minutes to a couple of hours, it triggers small earthquakes that we can see as those seismic swarms. And then we have the third layer that is mantle part of the fault beneath the 600 degrees isotherm, and that just slips freely because it doesn't have, it's not capable of seismic slip at all. We think that the fault is loaded from beneath, so both of these layers are actually loaded from the mantle part of the fault, but also the crustal part of the fault is loaded actually by that middle layer that loads it episodically. And we think that the loading takes several years, and there might be several tens of episodes of the creep, but we think that actually what we observe, like that seismic swarm before a large earthquake, is that it actually reaches a limit. That last episode of creep reaches the limit and actually triggers a seismic slip in the crust that then propagates all the way and releases the rest of the slip in the mantle. So that's pretty much what we think how it works. One kind of interesting fact, I was at AGU this year or the past year on Christmas, and I saw this poster of a girl from England, and she was studying a fault in Cyprus that was lifted up, and actually she could take some samples, and it was purely geological study, like something that I have very little or no insight into. But at the final model, she actually, I'm very sorry for the quality of this picture, but I just took a picture with a cell phone of the whole poster. But she formulated this model in the end, and she has a crustal part that is seismically coupled, and then conditionally stable mantle part, and then some dry kind of locked patches on the mantle part of the fault. So it was kind of like finding a missing twin after 30 years of not seeing each other, because it was completely two different pathways, but we got pretty much exactly the same result. So not that I wouldn't believe my results before, but it was still very nice to see something that kind of confirms the model from totally different perspective. So it was quite fun. And with that, I would like to move actually on and show you something that I'm working on right now, although I shouldn't be because I need to defend soon. And those are these whale seismology things. So as it turns out, I had no clue about this as a seismologist, but oceans are full of whales, and those whales make sounds. So I would like to show you some of those sounds. So this was a humpback whale. Now moving towards a little bit more boring ones from a listener's point of view, but more scientifically interesting ones. This is a blue whale. And one more that I am actually working with is a fin whale. I mean, it's more fun than it sounds, probably. So having a look at my data in my seismometers, I found, oh, I'm clicking somewhere else. I actually found hours or hundreds of hours of records like this. This is 1 hour of recording on 4 components. It's a vertical up there, 2 horizontal components on the seismometer, and a differential pressure gauge in here. And those are frequencies that don't really interfere with our earthquake stuff, so I haven't seen them really before.
What does it mean, these gaps?
Oh, yeah, these gaps. So okay, I will reveal it. These are fin whale calls. And how the fin whales, I'm not a biologist, but as up to my understanding, yeah, this is a briefing actually. That's when they, so that's when they like surface to take a breath, and there are like, I don't know, maybe 30, 50, it depends, calls in between those breaks. So, and people actually, when you do some Googling, people have done a lot of work on sounds like this, both on seismometers, which is slightly less usual because people normally deploy them for earthquake purposes, but people have also tracked whales based on OBSs, based on ocean bottom seismometers. But people have done a whole bunch of work with just pressure gauges deployed somewhere on buoys in the ocean, recording whales, tracking them where they are. So, as I'm saying, these are fin whale calls. People know a lot about fin whales. I have no clue about them. I just know that they are very long and very heavy. And I don't really, if you care more, you can Google something more about them. There's about 70,000 of them worldwide. Those are estimates. So those numbers are estimates of fin whales in the ocean. They are populating pretty much the whole world, except some like very north situated areas. And they migrate seasonally. So they go for winter when polar areas are really cold. They go in equatorial waters, and then they migrate for the summer. They migrate to polar regions, so they feed and breed, and I think they just like chill in as we do normally during the summer. And the same they are doing on the northern hemisphere. It's quite an interesting fact that although they pretty much do the same on the northern and southern hemisphere, because the summer is different time, like half a year later on the southern hemisphere versus northern hemisphere, these two populations of the same whales, they never meet, because although they are in the same waters, in equatorial waters, they're delayed. So they actually developed to two different species now, and the southern ocean, or not the southern ocean, but the southern hemisphere whales are now a little bit different than the northern hemisphere whales, although they are like meeting in the same place, it's just different times. When we close up on those calls, this is a frequency and this is a time domain section of a call or vocalization that takes about 30 minutes. And in here we see that every 20 to 30 seconds there is a call. In frequency we see that it's actually not the same call, that one call repeats every minute, and every like half a minute after there is a higher frequency call. So one of those calls is about 15 to 20 hertz. The other one is about 20 to 25. Those calls are really strong. It may be up to 186 decibels. Comparing to ergon, ergon is actually more. It's about 210 or something like that. But still, these are one of the strongest sounds in the ocean. So they can be heard over 100 kilometers distances. And actually, when we zoom into one of those calls, it looks like this. It's 1 second call that is downsweep in frequency. So it's from, for example, this is the higher frequency one that downsweeps from 25 to 20 hertz. And it reminded me something. It reminded me vibrosize that actually does upsweep motion in frequency from some 10 to 100 or 80 hertz or something. So I would like to introduce you whale size, as I call it. And whale size works the same way as vibrosize does. So when we actually have some waves coming, penetrating the ground, it bounces off layers. There are some reflected waves from different boundaries in the Earth. There are some refracted waves that can travel longer distances, but they are smaller amplitude, of course. And because we can't really take whales on the ground, and vibrosize cannot work in the ocean, people normally use air guns. So they just come with boats and like blast those air guns and record it on either streamers on the surface of the water or ocean bottom seismometers. And I'm trying to do the same with actually whales. It's the same principle. The principle is quite easy. Doing it with whales, I had some challenges. So first of all, I had to do the localization of those whales. So what I'm using for that is that this is like a 5-second or so record of the whale call, and we see like one big, 1 second pulse, and something that comes somewhere from 1 to 4 seconds later, and that's the first multiple. So the direct wave comes from the whale straight to the station, and the first multiple bounces off the ocean bottom, the ocean surface, and comes to the station. So based on primitive trigonometry, we can pinpoint the distance from the station. And I've tried to do location based on different stations in the network, but actually what turns out to be the most stable solution is that I actually locate whale only based on one station, based on polarization analysis. So when the sound comes to the station, it kind of shifts the station in the direction from where the sound is coming from. So for example, for this plot, it would be coming from either like a northeast or southwest in here. So that the direct wave is always polarized like this. And so we know quite well the azimuth where it was coming from, but it can be still like either this direction or that direction. And then because we know, we can also do the polarization analysis with a vertical component, and we know that there are no whales underneath the ground. So the sound is actually coming like from the top. So it pinpoints like one or the other. So this is the whale location or like whale travel path around the station that I'm using just for an example. So it's this station BS080 in here. It was a whale sequence that captured about 16 kilometers of the path of the whale and contained about 400 of those high-pitch calls. I am using just those high-pitch calls, although I potentially could use both of them and increase the signal-to-noise ratio, but because there was actually higher noise in the lower frequencies, I'm using just the higher pitch ones. And this is the result when we actually plot them as like call getters, analogically as shot getters for reflection seismics. And we display the vertical component of the seismometer and the transverse component, which changes the orientation based on the whale location. And I used just this is just a proof of concept. This is just a proof that the data are there. So I didn't use any fancy inversion or anything, but just like a waveform, like a travel time modeling, forward modeling. So I actually iterated quite a simple oceanic crust structure as I expected it would look like, and I was changing velocities, I was changing the depth. And so this is the ocean, the blue, and then we have some sedimentary layers that are often on the ocean bottom. Normally they are like 500 meters thick or so, and then there is the basaltic basement, layer 2A. And we approximately know what the velocities are supposed to be. So when I put two layers in there with these velocities that are in here, and I calculated arrivals of P waves and conversions P to S that I expected to have more on the transverse component in here, it actually works out quite well. So what we can see here, this is a refracted wave from the basaltic basement. So that's a wave that is coming from the whale, comes through the layer 2A and comes up to the station, which is situated up here. And then we have those reflected waves. Same, the PS conversions are here. This is the PS conversion that is coming from the ocean down to the basaltic basement, up to the station, and so on, and so on. So this is just showing that the data are there. I actually don't know whether it's useful or not. So that's one of the questions probably to answer. Is it actually useful, or should I have been doing something else these past 2 months? And of course, like if somebody wanted to pick it up, I think there might be something about that. Pretty much every single step that I have done can be improved. Location, signal deconvolution, I was using 1 second of that direct wave to deconvolve the signal. So I was actually getting just the reflections. But somebody who is actually more skilled in reflection seismics can do a better job. And also, my advisor was kind of like pushing me a little bit because the funding is coming from something that is not really meant for whales. But I suppose it's life. Or we can use whale arrays to increase signal to noise ratio. Like here, these beluga waves. So yeah, with that, I would like to thank you for your attention. I would like to acknowledge actually John and Jochen Braun-Miller, who planned all this project. They did most of the field work. I came to Oregon after most of the data were already collected. The funding was coming from National Science Foundation, and there were so many technicians and volunteers on those boats. If you are interested in details, or if I was too cryptic about some things, please see the paper, and I can play some more whales actually. Just to wrap it up. Yeah.
Well, thank you, Václav, for what ended up being 2 talks for the price of 1. So I think there'll be some questions.
Or suggestions. I'm taking suggestions for the whale stuff too.
From the seismology community.
May I give you a question, but not about whales?
Well, okay. Yeah.
So, first of all, congratulations for perfect research, nice presentation.
Thanks.
And first of all, paper in Nature Geoscience. I like this great obvious deployment, and wanted to ask you why you focused in this paper just to Blanco age. You write in the end of your paper that Blanco age is special in its large seismic coupling. Do you expect some continuation of research using also Western part? Do you expect completely different results because there is not so many earthquakes? Or what was the motivation to focus just on Blanco age? Is it some maybe less abundant data in the Western part, or different physics, or what?
In terms of number of earthquakes, it's similar to other parts of the fault, but it's much simpler in the structure. So we have only one single fault that is very clear from the crust to the mantle. It goes straight for those 120 kilometers or so, and we have only one fault. And what's different actually on those other parts of the fault is that those pull-apart basins are much more complex. They have multiple parallel transfer faults, some seismicity in between. So I think it would be actually, yeah, we will continue in those parts, and I'm expecting some swarm events too, and stuff like that. But I think it's more complex. So, yeah, that complexity complexity was the reason why we didn't. And also, like, those parts are like every single one is slightly different. So for that paper, we concentrated on just one part because it was enough material already, and we expect them to work a little bit differently than this one.
You showed the p-values along the fault. Yes, it was mostly around the 1, typical for the major applications. But one segment, for one segment, there was p-value about 10, about 2, 100. 1.8. What is the reason for this Cascadia?
That's a good question. I don't really know the reason. It's probably because I'm more guessing. I think that we can see many like earthquake swarms in there, and I think those might be also triggered events by some kind of a process.
Is it this engine characterized by trolley shocks and or swarm seismicity?
These are like almost uniquely swarms. There are no foreshock aftershock sequences. So Yeah, I think that there will be probably some kind of triggering mechanism in there, but I haven't done any detailed analysis yet to constrain that.
And the other question, how do you distinguish between foreshocks and swarms? Because you said that both precede the big events.
Yeah, I probably wasn't clear about this. I think they are the same thing. I think that people actually formally as they didn't have, like, this is a second deployment on Oceanic Transform Fault, and by far the largest one so far, and people didn't have that resolution to like see that there might be like more common swarms and stuff. So when they saw some foreshocks, they thought that those are foreshocks, but those were actually swarms that were just preceding the earthquakes. So I think those are one and the same thing. Those are not actually different. Yeah.
Thank you.
Your depth distribution of the earthquakes showed a maximum around the pole moment. Not many earthquakes in the shallow crust.
Mm-hmm.
So if I understood you correctly, that is maybe because in the limited observation time of 1 year, you basically only see the conditionally stable behavior where you have some episodic week that triggers this whole earthquake behavior.
Mm-hmm.
Whereas the uppermost part is basically fully or nearly fully locked and is waiting for the big earthquake. Is that correct?
The uppermost part is fully locked, but it's not just like waiting and releasing all the energy in one earthquake. It's just like kind of a normal, not normal fault, but like normal fault, like with V value equal of 1. So there are plenty of small earthquakes, but most of the energy is actually released during the large one, because if you have V value of 1, the amount of energy that those small earthquakes release is actually negligible. So the upper part, I think, the crustal part is like a normal kind of fault, and then yeah, the mantle is kind of like those swarms with different V values and stuff like that. But this is actually all those 8,000 events in one plot, and it's mixing apples and oranges. This is just like the first display of it. But
the first order would mean that at around low depth or uppermost mantle, you basically here in this plot, you see the background mode that is always there.
the background what, sorry?
Some kind of a background mode that you basically don't store up energy while you're recording from here. But you release not everything scientifically because some of it is free, but you don't basically store energy for later, whereas in the uppermost part, most of the energy during that recording time will be stored.
Yes, in the uppermost part, or like in the crustal part, most of the energy is stored. In the lower part, there is certain percentage, about those 60% that is being stored. Or no, the other way around, sorry, 40% is being stored.
If I understood that, 40% energy, strain energy has been released, seismic events, and 60% in aseismic. How did you estimate this ratio?
So it comes from the magnitude 6.5, and we got quite nicely constrained the centroid depth for this. That was right above the MOHO. And from those ratios, you know that centroid depth releases half of the, it's kind of like a, I'm not saying it exactly correctly, but like half of the moment is released above it and half of it is released beneath it. And knowing the lower limit where the slip probably stops, and those 12 kilometers where the 600-degree seismotherm is, we can kind of constrain. It's kind of a back-of-the-envelope calculation. It's not very precise. But for this purpose, it's just to get a rough estimate of what the coupling is. I think it was good enough.
In the supplement, you show figure where there are parallel Markov seismograms. You used it for deriving PVS velocity ratio, but I did not understand very well. Did you locate it from P and S?
Only from P's. Yeah, from P's. Yeah, we didn't use.
So you located from P, including the depth, but then, of course, you made some kind of checking.
Yes.
In order to define this gap between uppermost part and lower part of seismicity.
Yeah. It was just for the purposes of showing that that gap is there and that those depth locations are trusted.
This incredible, let's say, seems very reliable from people. For me, it was surprising getting such a...
Of course, it would be ideal to include SS2, but first we don't really have like such a good velocity model. So I don't...
This is another question. You changed velocity model by 3%, by roughly 3%, you said. So did you do it in the whole model for all that? So you write different parts differently just to fit the data?
What I actually changed was the mental, upper mental velocity by 3%, because I saw that the P waves, we have so many PN waves in there, because the crust is so shallow, so the crustal events turn to PN waves really quickly. So we have very well, like that's something that we have very well defined is actually the mental velocity. So I changed that because I saw that's kind of like that's not very well constrained in that older model. So in the newer one, I changed that. But the thing is, we probably need like some tomography to get like a 3D model. And then yeah, it's yeah.
I have a question related to the estimate of 600 isotherm.
Mm-hmm.
Do you have also some data or information about estimates based on magnetic data?
No.
No. Because 600, that's the Curie depth, and you can get it also from inversion of magnetic data.
Oh, okay. Yeah, I wasn't aware of this, so maybe that would be something that you can tell me about. Thanks.
From when this magic value of 600 degrees come, I did not understand, because first I thought that, well, there are some earthquakes below the 600 degrees isotherm calculated, including the hydrothermal circulations, so there are events below. But for me, this means that either this model of, let's say, thermal development is not complete, or 600 is not so, let's say, well-defined limit.
Yeah. So yeah, no, that's a very good point. The thing is that the 600 degrees was derived from lab experiments of Margaret Boucher, and she's saying that it's kind of like the most reliable like thing that we can like pinpoint at this moment. It may be a little bit more, a little bit less, but in terms of actually like it's not going to be 500 and it's not going to be 700. So maybe the brittle duct transition is slightly off 600 degrees, but for...
But you need probably less than 600 because of your circumferentialization. You need circumferentialization for slip, for free.
Yeah.
This is very important, probably.
Oh, well, I don't need 600 for the creep, because when it's serpentinized, the serpentines creep even below the 600. That's kind of the... yeah, in here. It is, you're right, this can be, you know, if actually the brittle duct transition wasn't 600, but it was 550, it would be like somewhere like up here, or like a little bit lower if it was higher. It is a little bit like a chicken or egg kind of question. I think that in the main contours, it's not going to change the results or the conclusions. But there are like each of those numbers also like there is some uncertainty in depth determination that we, you know, I wouldn't fight for, you know, a kilometer up or down, claiming that the brittle ductile is at 12 and not 11. But kind of the major point is the dichotomy between the crustal and the mantle part. So I don't think it changes much. But you are right that this is something that, yeah, like what number do we actually trust?